My name's Bart Machielse. I'm a quantum research scientist at Amazon. And the part of Amazon I'm in is the Center for Quantum Networking. So the Center for Quantum Networking is a research arm of Amazon that is trying to bring quantum networking technology to AWS customers. And quantum networking isn't something people think about, but I did a PhD in the subject, and so did most of my team. And so we sort of have a unique expertise in identifying the materials, the protocols, the technologies that will make it possible to distribute quantum information over long distances. And if this works, we think it can be a security enhancing technology for AWS, in addition to enabling a lot of new types of computation and sensing and nice information processing protocols. So we're really excited to develop this technology, and one of the avenues we're exploring is via Diamond. I think perhaps the fundamental challenge in quantum networking is finding the right host material emitter pair that has properties that make it viable for real-world deployment. So the sort of core element of a quantum network is a quantum repeater, and the core element of that is a quantum memory. And so really the function of this memory is to basically catch information that's propagating on light, store it on the memory, do some simple processing, and essentially enable it to be propagated further. So for a memory to serve this purpose, it needs to really effectively interface with light. And we're talking about single photons, single bits of light, and needs to be able to capture the information that's stored on that light and save it for an extended period of time. And this probably sounds like a complicated endeavor, and in some ways it is. And so people have spent 20 plus years looking for the right quantum memory, and the search is still ongoing. I want to be very clear, but one of the very promising candidates are quantum memories in Diamond. So really what we're looking at here are these sort of substitutional defects, the nitrogen vacancy, the silicon vacancy. These are things that I guess a lot of serious Diamond people are already familiar with in some capacity, but it's basically an atom plus a couple of vacancies that have combined. And these emitters have really cool properties. They have long memory times, and they interface really effectively with light. And so, those are the two main requirements for a good memory for quantum networking. But Diamond also has a lot of other nice properties, right? It's not sort of a standard CMOS material, but it is, in principle, processable in many of the same ways we do process semiconductor chips. And that gives it another added advantage that, it hosts these cool memories by default, and then you can really carve the Diamond into whatever configuration you need in order to facilitate sort of optimal operation of this memory. And it's really those properties together that make Diamond very interesting. It has a few drawbacks, of course, but its strengths are it naturally hosts good memories, and you can, shape it into photonic and electronic devices very naturally using already existing tools. As you pointed out, we definitely have to use synthetic diamond. Natural diamond doesn't have the purity anywhere near what we care about. But even among synthetic diamonds, we have very tight impurity constraints, and we need, very pure single crystalline diamond. And so there actually aren't very many artificial diamond growers or synthetic diamond growers who offer this product. We've tested a few dozen over the years, and finding someone who can produce what we consider the base substrate, really sort of the fundamental piece that we build everything on top of, is pretty challenging. That's why this relationship with E6 has worked out well for us. They've delivered this in the past. But what I said is the base substrate is available now, right? If you go to a small number of suppliers in the world, they'll be able to produce this quantum electronic grade diamond. But we want to go even further. We want sort of fine control over dopants. We want control over morphologies. We want finer control over crystalline properties. There's a whole list of things that we need in order to make this technology a slam dunk, really position it to scale very effectively. And that's where the sort of continued research into plasma enhanced CVD diamond growth is very valuable to us. And that's really something we're interested in. Definitely think it's relevant for us, right? I would say very clearly that any type of serious information processing will generate a lot of heat. And whether you're doing this at room temperature for in a data center where you're making billions of computations per minute, or if you're trying to do your sort of quantum networking experiments inside a cryostat that has very finite cooling power, being able to effectively get the heat away from the sort of point where it's generated and sort of spread to the rest of the chamber where it can be sort of controlled more effectively is an important part of our process and is something we think about a lot. So for sure, thermal properties of diamond, electronic and optical properties of diamond, sort of these fundamental things that make it a cool material are also very relevant to quantum applications and other photonic applications across the board. I really think that we're not far from the point where private and secure information transfer sort of facilitated by these memories. I think that's possible on the relatively short term. So basically the formation of these quantum repeaters and sort of propagation of information. And I think that is something people care about a lot, right? Like for AWS, right? We always say security is one of the main focuses. And I think making sure that we have all of the resources at our disposal in order to do this information propagation effectively, that matters to us a lot. So I think that's the first block. But I think the further out you go, sort of the more exciting things get, right? So quantum computation is a very, very difficult problem. And I think anyone who claims to tell you that they know exactly when and where and how this will come together is very optimistic in their own knowledge. But I think it is going to be part of the story going forward. And quantum computers get a lot more interesting when you can manage the sort of information transfer in and out and between sort of on a quantum level. And we really think that this is another place where the ability to propagate quantum information over long distances is very interesting. So, again, we have what we think are sort of an interesting, compelling short-term argument, and we're very interested in seeing how this technology evolves as the field continues to mature.